Marcel. So are you ready, Marcel, to get started? And I'll just do a little intro.
I'm good to go, yeah.
All right, so let's just head up. Welcome, everybody. This very first OpenShift Commons AIOps SIG meeting. If you haven't yet joined the Google group, the link is there in the HackMD note to join. That's what we're going to be using for our open mailing list for the group for Q&A and sharing resources and events and other things. If you don't know me yet, my name is Diane Mueller. I am the Director of Community Development for Red Hat for the cloud platform, which means lots of different things, OpenShift operators, and all the workloads that run on OpenShift and all of the related upstream projects I get to play in, such as Kubernetes and the CNCF stuff. And my colleague Marcel Hild approached me, about a month or two ago about setting up this SIG. And so I'll let Marcel introduce himself and we'll go from there.
Okay, let me share my screen. Oh, there it is.
There we go. I think I have to stop sharing.
I thought I can take over. Now you're all spoiled. Okay, can you see my screen? The red one?
Absolutely. Yep.
Absolutely.
Looks great.
Cool. So, thanks, Diane. My name is Marcel Hild, and I'm working in a group of Red Hat's Office of the CTO called the AI Center of Excellence. And obviously, we're looking into all things AI related, and I'm specifically focused on the broader theme of AIOps, what it means for Red Hat and the general community. So in the past years, we managed the problem of ever increasing demand for computing power and applications in general by separating the concerns inside the data center. We needed to support a high-paced environment asking for agility in application development and operations. So changes to applications were driven by the developers, and they changed their systems multiple times a day if you look at continuous rollouts and continuous deployments. So what we did, we disconnected the components and brought them together via microservices again. And if you look at it, the same concept applies throughout the whole stack, like distributed compute, distributed storage, distributed applications, and orchestration of services. And with cloud-native tooling such as containers and Kubernetes, we're basically able to infinitely scale out. And obviously, this comes at a certain price. More components mean more complexity. But then, hey, in IT operations, in the DevOps world, we need to know when something isn't working. And we need to know it now because we've committed to those 5 nines of uptime SLA and stuff. So to control these complex systems, we need to introduce some sort of instrumentation, some telemetry is required. And so we produce more metrics, more logs, more stuff. And again, we do this at every layer of the stack because every persona brings different needs. Developers need stack traces. Operation folks need latency and timeout metrics. So how can a single human possibly comprehend such a system? We're creating complex systems of rules, alerts, and thresholds. And guess what? We can't keep up with updating our alerts because the systems being monitored change at a faster pace. So it's a classical cat and mice problem, so to say. But in our case, we're in luck because a smart person once said, every repeatable human task that is governed by a probabilistic relationship between input and output, will be subject to automation at some time. And to be fair, with all the AI hype nowadays, that's the current state of the art, where it boils down to precisely exactly this. We're training the computer to do very specialized tasks. We excel at seeing patterns in huge piles of data with millions and millions of input features, and to the uninitiated, it might look like magic, but at the bottom it's a classification problem. If input A, then output X. And actually we're doing this in all these fields that have a great and powerful monetary background, like showing you the most relevant cat images, or with a great media coverage, like beating human players in almost every game out there. But what about operations? What about ops? And I think here we're just starting to apply all these techniques to our very own special field. So in other words, if your website is slow because your storage is slow, a computer can tell you that. And even better, if your website is slow because somebody flipped a bit somewhere in a not so distant system, with sufficient input and with sufficient training data, a computer can also possibly tell you that. Yes, your website is slow, and if you flip this bit back, it's going to be fast again. So what's AIOps anyway? Gartner coined this term like some years ago, and it goes like this. AIOps platforms are software systems that combine big data and AI or machine learning functionality to enhance and partially replace a broad range of IT operations, processes, and tasks, including availability and performance monitoring, event correlation and analysis, IT service management, and automation. There's a lot of words in there, and I've provocatively highlighted these words: AI replaces IT operations, because people tend to think like this, but like it replaces truck drivers at some point. Although the self-driving cluster will probably be marketed sooner than we think, I don't think that IT operations will be replaced anytime soon. But we will certainly use big data and machine learning to support our monitoring and automation needs. It's just that. It's just another tool to make you more effective and efficient, a tool to support us and not to replace us. And indeed, this is something that we as Red Hat believe in, and we are invested in it. This is another good quote from one of our team members: the key next step for systems management and software development is the replacement of heuristics and fixed limits with learned models. That's by Ulrich Trepper, also from our CDO office. And so not only for operations, but also in our development processes, we have to apply that piece of machine learning supports too. Again, this is how Gartner describes an AIOps platform. At the center, there's big data and machine learning, and then it's a cycle of continuous insights being delivered to these three domains here. Monitoring in the upper left corner will benefit from smarter alerting and like dynamic thresholds as seen before. The service desk will move from a reactive to a more proactive engagement model, with higher efficiency when it comes to troubleshooting and stuff. And ultimately, your actions are highly automated, and at some point with less and less human interaction. And I think this perfectly aligns with the four phases of AIOps. So first, without data, you're nothing. So data is the new oil. And so we need to get our data collection straight. We need to make sure that we have systems that emit the required telemetry and that we're able to store it for a longer term than just your 2 days of retention period. Plus, you need some tools for visualization. Via images, you convey meaning, and a log file entry that might be obvious to you, the author of that log emitting system, But what about all the metadata in that entry? How do you paint a broader picture over time? Then we need some tooling to help us discover patterns in that data and help us understand these patterns and correlations. Because, I mean, make no mistake, there won't be a one-size-fits-all solution for everybody. You will still need to assist the computer, and the computer will support you in your understanding of that problem domain. You're still in the driver's seat. And after learning from the past, you want to apply your knowledge to the future event, to some future events. You want to know that your application needs to scale out before you actually hit all that traffic. And last but not least, you finally want to know the reason why something is failing, like on the spot or post-mortem. This is the classic needle in the haystack problem. Let the computer guide me to that flipping bit that caused my outage somewhere. And I think what we're all currently missing is a larger community for AIOps. So in every emerging technology, we're seeing a multitude of projects and products addressing similar problems with different approaches. And I mean, this is good. Variety is like the spice of life. But remember the complexity of our problem space, like how many components need to talk to each other. And I think so we need also to be at least aware of each other, discuss and share our experiences and our reasoning why we took specific approaches. And then by finding ways to collaborate with each other, be it by integration of projects or products, or maybe even creating open source projects that solve a common problem, and ultimately leading to standards that define the way our machines collaborate, like standards how to run things, standards how to talk to APIs, or how we store and query data. And I think here we can build on the success of the operations community, where slowly standards like open metrics or open tracing are emerging. I even think we can accelerate the speed of adoption of such standards and common open source tooling by having a voice in the definition of such standards. And I think a SIG is a great way and place to do such a thing. And with that, I would like to open it up for discussions.
So thanks for setting the stage, Marcel. I think it's very helpful, and the Gartner definition has definitely flavored a lot of our conversations recently, and helped to give a little focus to this space. Other folks that are on the call, different definitions that you might have, or different outlooks on AIOps. And if you're trying to speak, just unmute yourself. And you should be all unmuted. Or raise your hand in chat. All right, we're having quiet time right now. So maybe what we'll do is we'll just move into the next presentation. The sort of style that we use for SIG meetings here in the Commons is I and Marcel as chairs will ask people to come and share their perspectives to sort of spur conversation and to do some background education. And today we have with us two folks who have been doing a lot of work in this space from Siscale. Bogdan is our next speaker, and he's going to talk a little bit about ARCANNA, and I'll let him explain that. It's a long acronym for some interesting work that they're doing at Siscale. So Bogdan, if you'd like to share your screen, and we'll just kick off.
Thank you. Just 1 second.
1 second. And if you haven't yet added your name to the list of attendees, in the HackMD, please do so, or if you could add your affiliation in so that we know where you're coming from and your perspective.
I will as soon as I finish the presentation. So hopefully everybody should now see a very big screen saying ARCANNA.
Yes.
Definitely.
That's great. So hello everyone. My name is Bogdan. I am a principal solution architect with Siscale, and I'm here to talk to you about a solution that we at Siscale have been developing. It's called ARCANNA. It's a short name for a very long, an abbreviation for a very long name, actually. Automated Root Cause Analysis, Neural Network Assisted. Before we discuss what ARCANNA does, I want to tell you why we started work on this project. And just to give you a little bit of a background, I am a networker and a sysadmin. I started working with computer networks a while ago, a little bit over 15 years ago. And I've gone through CCNA, CCNP, CCIE. I've moved on to data center virtualization. And then it was only a small step to move to operating system virtualization, to container technologies, Docker and Kubernetes. And during these years, I've seen the same process again and again. I've seen what happens when something isn't working. What generally happens here? Somebody gets notified. You get an alert. The apps team says, nope, it's not us. It's the network guys. The network team, it's not us. The server is the issue. The server team, of course, not us. It's the app. A lot of time passes. Nobody knows where the issue is. Nobody, maybe hours later, nobody even knows where to get started on fixing that issue. And the problem here was very well pointed out by Marcel earlier. It's, I wanted to use this image. I wanted to talk about searching for a needle in a haystack, but I think Marcel put it much better. It's a cat and mice game, and the mice are multiplying like crazy. Just a few years ago, you had your physical server and you had your application. If you had a problem, it was the network, the server, or the application. Now you have the hypervisor. Now you have the container. You have the container orchestrator. You have storage that might be local or it might be over the network. You have much more places in which something can go wrong. And identifying the true culprit when something does go wrong is becoming a more and more difficult task. But we also have some very nice, very useful technology that can help us. And since I don't know if everybody here is familiar with Elasticsearch and the Elasticstack, I will just do a very quick presentation of them. First of all, Elasticsearch started as a tool for searching through huge amounts of text. Even now, when you talk to an Elasticsearch cluster, it replies with, for search. But the truth is, it is no longer just for search. It is also a very powerful way of dealing with time series data. And nowadays, we are seeing Elasticsearch being used more and more for monitoring because it works very well as a kind of NoSQL database. You can just populate it with the time series data, the metrics that you want to collect, and then aggregate, correlate, work with those metrics. Also, around Elasticsearch, we have an entire ecosystem now. It's the Elastic Stack. It was originally called ELK. for Elasticsearch, Logstash, and Kibana. But then they added the bits, the lightweight log shippers, and somehow neither Belk or Black or ELBK sounded very well, so they decided to simply rename it to the Elastic Stack. So this is what we have. We have very powerful tools that allow us to collect the data. We have very powerful tools that allow us to centralize the data and put it in one place. But still, we still have two problems here. The first one is that the data comes from many sources. If you've ever had to collect information from multiple devices belonging to multiple vendors, you already know this issue. I want to know what user has performed a specific action, and all the actions are logged. But what is the field for the user? Is it user, username, user.name, nginx.access.user_name? It's very difficult to correlate data when the fields that are being used differ between different tools and different vendors. And this is where Elastic has come up with a very nice idea. It's called the Elastic Common Schema. It's an open source specification that defines a common set of document fields for data. Once you apply this Elastic Common Schema, once all your data is indexed in the same way, it becomes easy to correlate data from different data sources. So that's one problem that I don't want to say it is solved, but it is in the process of being solved. The second problem when collecting data is this one. This is an actual demo created by the people at Elastic. It shows real-life troubleshooting scenarios using Elasticsearch for a problem that occurred in an application. It's a basic application with multiple processes, multiple microservices making up that application. And at some point, we get an alert. And as usual, the alert doesn't say too much. Poor performance on the server. From there, we go into the dashboards. And without going into the details, we start to dig. We start to look what has happened. When has the problem started? Does it have a clear start and end point? We dive in. We look at the actual server application performance monitor. We look at the response times. We still don't see a smoking gun. All the response times are very long. We switch. We go into the containers. We dig a little bit deeper. We see that there seems to be a problem with one of the containers running on one of the nodes. We go into that container and we see some spikes on the CPU usage. We go there, and finally we look at the processes. We see that there is a backup process that actually runs at a certain interval, and everything becomes slow while that backup process is running. Sorry. Now, I went very quickly to all of this, but the problem here is that there are many sources of data, many places where something could go wrong, and many times we do not know where to start. We start digging, look at the servers, look at the network, look at the application. In the end, we will manage to isolate the problem, but it takes a lot of work, it takes a lot of time. And the question was, can we do things better? Can we improve the time it takes to identify the actual root cause? And we believe we can, because the problem here is, how do we make sense of the mountain of data? How do we use the machine to help us, to give us a starting point, to point us in the right direction for identifying the root cause? Enter ARCANNA. This part here is what we already have. This is Elasticsearch collecting data from our infrastructure. Everything in the infrastructure is monitored. We have telemetry. We have the information going into Elasticsearch. we can, with ARCANNA, we can do first event clustering. We put together the events that occur together, the events that probably have a common root cause. Then we try to identify the probable root cause for those events. And with that, we can engage the appropriate team. Once the problem has been solved, the feedback actually goes back into ARCANNA. We tell the system what has happened, whether the determination was correct or not, and the system learns from our feedback. How does it work? Again, we have our system. We have the Elasticsearch with all the data. We have ARCANNA, which is basically a plugin for Kibana, the data visualization in the console for Elasticsearch. And inside, we are running a TensorFlow supervised machine learning model that actually gets access to all the data. So the machine learning system looks at the data and tries to identify what the root cause might be. Again, to give you the full flow, what has happened? What are the events? What does the machine think that the root cause is here? Identify what the potential root cause is for this set of events. Is that enough? Is the determination correct? We don't know. Right now, it is not, but we provide feedback. After the troubleshooting steps have been completed, after the root cause has been positively identified, the user provides feedback for ARCANNA. The user tells the system, yes, you are right, this was the actual root cause, or no, that was not correct, the actual root cause was something else, it was that one. And the system learns, and all the data also goes back into Elasticsearch. And with this information, the system continually improves. With time, it learns to identify the root cause correctly. And this is what we have now. But what about the future? How can this system be used in the future? I need to specify that we are not there yet, but think of a future in which we can actually take action when we are reasonably confident that the root cause has been correctly identified. What if we are more than 80% sure that the issue was a backup process running on the database server? Can we go in and automate the solution? We believe we can. If we have a certain confidence threshold and we are above that threshold, we just go in, we run an Ansible script, the script goes to the server and takes corrective action. We might be heading to a point where the problem is solved before the users even notice it. It will not apply to all the problems, but if it applies to 50, 60, 70% of the problems, it will free up a lot of time, a lot of resources for the people actually doing the investigation. Now, just to show you what the interface looks like, this is the interface for ARCANNA. If you have ever worked with Elasticsearch, it will look very familiar because it is nothing more than another plugin for Kibana. This is where you define the machine learning jobs. This is where you tell it what fields to take into consideration for the ML job. And of course, you can also rename some of the fields if you need to do so. You can rename them from the interface. the ML job starts running, and in the end, we get an output like this. These are the events that were identified, and ARCANNA believe that these three are part of the same set of symptoms. They have the same underlying root cause. We have a web server reporting an internal server error, a 500 error message. We have a SQL server saying that it's unable to write to disk. We have a server that is out of memory. ARCANNA believes that this out of memory was the root cause. ARCANNA believes that we should investigate this particular server first. Is it correct? Is it not? We go in, we investigate, we perform our investigation, our troubleshooting steps as usual, and in the end, these are actually toggles. You can switch them between root cause and symptoms. In the end, you can go in and tell the system, yes, good job, or no, that was not correct, try to do better next time, and the system will improve. Keep in mind that there already is a level of machine learning in the Elastic Stack. Elasticsearch already has unsupervised machine learning that can already reduce some of the noise. It can detect only anomalies. It can detect when something deviates from normal. We are adding on top of that. We are adding the supervised machine learning component and the automated root cause analysis. So the tools that we have go up to step 3 that Marcel mentioned earlier. Now we are adding step 4, the automated RCA, automated root cause analysis. And of course, on top of that, you can add Flake, you can notify the correct teams, you can add playbooks for automatic remediation if the root cause identification is reasonably confident, and you can always provide feedback, and the system will learn from the feedback you provide. So that's it for ARCANNA. Of course, if anybody has any questions about the system, I will be glad to answer them. Just please don't ask me too much about the machine learning part. I am not a developer. A lot of that is magic to me. I will have to ask my colleagues who have actually written the code for that.
Well, fortunately, there are a number of your colleagues that are on the call as well. So if you have questions, please raise your hand in the chat. And Marcel, if you have any comments, please add them now.
Some of the developers are also in chat, so if you have any detailed questions about ARCANNA, they are the people to ask. I see Colin here in the chat with us, so I do have the people who can answer.
Yeah, one remark from me, and this is Marcel again. So I really like the setup that you are trying to plug into existing technology, because I think that's crucial, that you need to have your monitoring stack in place before you actually can put some AI or machine learning on top of it. So it nicely integrates with what people already have, but then improves gradually their solution. And I also think that the feedback loop is a very important thing that most people often overlook, because in the end, a machine can only be as smart as you train it to be. So maybe one question for your developers would be: is there a way, or did you analyze how much better the network got over time, and how much feedback was required to train it up to a certain point where it could reliably identify some of the root causes?
It's Kevin here. Well, currently we're not quite at that point yet, so I couldn't give you exact number of iterations. It largely depends on the data you give it, so we're not quite at that point. It's still, yeah, we're still at the start, let's say.
But I do have some good news here, and I forgot to tell you about that in the presentation. This technology will be open source. And as Colin has said, everything will depend on the size of your network, the complexity of your network, the type of data you're collecting, the type of issues you're encountering, how many of them are repeated, how many of them are new, and so on. But everything, all the code will be open sourced. So very soon, you will be able to take the code, implement ARCANNA in your own network, and see whether it works for your particular use case.
Yeah, that's a very good news, and I saw that on your other talk. Actually, one of our team members also prototyped a similar solution, and I see already some place for collaboration there. So we also plug into Elastic, and we train a model, not a neural network model, but a model of a self-organizing map to flag anomalies in log files. You're going one step further of actually pinning down some root causes. We're only looking at a stream of log file messages and want to detect something anomalous in the content of those messages. But given that two parties came to a similar design independently, I think that's a good proof.
All right, well, I don't see any other questions at the moment in the chat. And we do have one other SIG group member that's going to give a talk today. Brian Jeng from Prophetstor is going to talk about Diskprohet. So I'd like to share the floor with him. If you could take over the screen sharing, Brian, and make sure your sound is on, we'll kick that conversation off too. And please keep asking questions in the chat if you have it. And Bogdan, thank you very much for the presentation. If you could send me a link to that as a PDF, your presentation, I'll add that into the meeting notes.
I will. Thank you.
All right, Brian, are you in there somewhere?
Yeah. Can you hear me, Diane?
Yeah, I can.
Okay.
Bogdan might have to stop sharing his screen. There we go. All right, now take it over, Brian.
All right.
Here it comes.
You guys see my screen?
It's a coming.
It's coming. You should see
There we go. Oh,
PowerPoint.
there. Yep, and now we'll just go into full screen.
Okay. So I'm Brian. I'm an SA over at Prophetstor, and I'm going to be talking about Diskprohet. And what Diskprohet does is we use machine learning AI to predict future disk failures up to 6 weeks in advance. And additionally, we can also predict performance and capacity for up to 90 days into the future, as well as give correlation for the effects of disk failure between the node, application, and cluster. And our biggest use case right now is for Ceph. So I know that a lot of you might not be very familiar with Ceph, but all you really need to know is that it's a distributed storage system that's self-healing and fault tolerant due to redundancy, which makes it really good for big data storage. And you can kind of extrapolate this use case to all distributed clusters. So in 2016, we partnered with another big company that actually presented at Red Hat Storage Day in Seattle that wanted to do a petabyte Ceph cluster for OpenStack Cloud. And they found there was 3 major stability issues with the Ceph cluster that was sort of blocking their project. The first one was that every time a disk failed or an OSD failed, the map would change, the crush map, which would cause placement group peering and backfilling, or the cluster would rebalance to heal itself, but then this would take up cluster resources and the client would receive slower performance. The second issue was that the data distribution wasn't balanced. The cluster had no visibility of the underlying disk capacities. So if you had different capacity disks in your cluster, some disks might be at 90%, while the cluster was only at 50% full. And then the user wouldn't know until one day the OSD just couldn't be written into anymore because it was full. And then the third issue they found was that one slow disk, a single slow disk, would affect the performance of the entire cluster. And then this would just continue to drag on the performance until it was ejected because the cluster had no visibility over the health of the disks underneath. And so they proposed a solution with our Diskprohet prediction, which was much less mature at that time, but it essentially did the same thing. We could predict disk failures 6 weeks in advance. And then they drew out all this architecture stuff. But the most important thing is this graph at the bottom right. You can see that there's a normal workload here of around 400 or so IOPS. And then when they simulated a disk failure by just pulling a disk, they found that the cluster performance dropped below 200. So they dropped around 40 to 50% IOPS and persisted that way. Oh, sorry. It persisted that way for the whole duration of the test. So 800 minutes, around 12 hours or so. Versus with our disk prediction, you can see that with being able to know a disk is about to fail in advance, we can take preemptive measures. We can disable the cluster rebalancing, and then we can remove the disk and replace it within an hour and have the performance go back up to a fraction of the time, in a fraction of the time, right? And then the same company tested our prediction engine against 20,000 drives over the course of 90 days. And they found that we had an accuracy rate of 96% and a recall rate of 97%. And the recall rate is actually the more important statistic here. It's the number of correctly predicted failed disks over total number of failed disks. So out of every 100 disks that failed, we would correctly predict 97 of them. Okay. And then this just shows that we're already integrated in the Ceph community. We're called the disk prediction plugin. You can just enable us through the manager daemon, and then you can just use Ceph native commands to access our prediction. And yeah, so we released with Nautilus. For older versions of Ceph, you would use this one-line installation, and you can use that with Ansible, Chef, Puppet, any kind of automation software to make it simple for mass deployment. And our biggest account right now is actually in Michigan. There's 3 universities: Wayne State, Michigan State, and University of Michigan. And what their setup is, all 3 of these campuses share a single giant Ceph cluster, and they put all their research data on the Ceph cluster. So they have to make the Ceph cluster as resilient as possible. And so what we provide is just the disk predictions and allowing them to monitor the health of their disks before they fail. Right. And I'm just going to go through a quick live demo. I'm going to switch screens here. Can you guys see my web browser?
Yes.
Okay. So what we have is just a simple software as a service cloud login. When you go and you see a dashboard, and it just gives you a really quick overview of how many disks are being monitored, how many are good, how many are bad, are going to fail in less than 2 weeks, less than 6 weeks. And you can go to the disk health list here to get a list of every single disk that's being monitored. And then you have all the unique identifiers and which node it's on, the size, the serial number, the vendor, all over here. Oh, sorry. All over here, so you can see that, so you can easily identify the disk. So, yeah, so this would be where you would go for the disk details. And then we also, I alluded to it earlier, we also have prediction for capacity and performance. So over here we have the cluster capacity, but we also go down to the OSD level. I'll just use pools because it's more interesting. And then we can predict future capacity for up to next 90 days. But of course, this depends on how much data you have. So the general rule of thumb is for every cycle that we predict, we need 3 cycles of that data. So if we can predict 10 days into the future, we would need 30 days of data, right? And yeah, that's about all we do. That's the end of my thing. I just have some screenshots.
Awesome.
Thank you.
This is great. The other thing, can you maybe step over to where that Ceph plugin is for disk protection, so that we have the URL in front of us while we're.
Oh, yeah. Okay, actually, I can just go into it in my disk prediction.
I didn't realize that it was a plugin already to Ceph. So yeah, that Ceph is kind of near and dear to our.
We work with Sage, the creator of Ceph, and he got us in there pretty quick. So pretty good.
Great to know. As we've got a lot of Ceph folks using Ceph and here at Red Hat and elsewhere. So
Yeah.
All right.
So one interesting thing to note here is that you can run the prediction in the cloud or local. So you could also run this setup in a completely non-software as a service environment as well.
Yeah, because in order to be with Ceph, they wanted like a lightweight version of our predictor, and then so we just gave them like one with less baggage that would be only 70% accurate, that they could enable locally, but it wouldn't use all the metrics that were provided for the prediction. It was requested by them to have a local lightweight package.
Okay.
Yeah.
So once again, I'll unmute all, and if you have questions, please ask them. I'm going to switch over and share my screen.
Okay.
So I have the notes here. Share. And you may all notice that I've added as many names as I recognize from the chat into the attendees list. If I got your affiliation wrong, please pop into the HackMD notes and correct me. We're almost about 10 minutes left, Marcel, and I'd like to talk a little bit about some of the goals for this group. One is we're just trying to reach out and build the community around AIOps here, and make sure that we have some of the resources that people are looking at and requiring. So thank you both, Bogdan and Diane, for sharing your insights and your tooling. It's a great start. And if there are other topics that people want to talk about or present on, or questions you have, please reach out to us. Again, sign up through the Google Groups and ask for those. If there's anyone here that and I'll look in the chat, that has any questions, I'm not seeing any. I'm hoping that some of you will have some suggestions for upcoming topics, and we can move forward. We're planning on doing this on Mondays at 9 o'clock, aka the time we started today, over the next few months, and doing it once a month, and trying to pull together something at Red Hat Summit, which is in May. If you're interested in having maybe a lunch and learn on the topic, we'll all be in Boston at that time. As well as I'm looking to host what we call an OpenShift Commons gathering, which is our face-to-face time for OpenShifters and people in the Kubernetes in ecosystem in the Bay Area sometime around September. So if you're interested in getting together then, please reach out to Marcel or myself, and we'll start coordinating a face-to-face sometime probably in September on this. So Marcel, if you wanted to add a few more words in here, I've added a few resources down the end. If everybody could send me PDF versions of their slide decks to dmueller@redhat.com, that would be great, and I'll add them in as well. Marcel?
Yeah, I'm just really excited that we gathered so many people, also not only from the presenting companies, but also from other companies in this first kickoff meeting here, and I'm really looking forward to extend that to other people in the community, to enlarge this community or to create a community. So once we have our website up, please make sure that you register your email there for additional updates, or go to the Google group that we have there so that we don't miss any of the sessions that we hopefully continue to do on a monthly basis. And I'm really looking forward to collaborate with you on GitHub and in an open source way. That's all I have.
And it's great to see so much of this stuff from Siscale and from Prophetstor being done out in the open too. So this is great, and we look forward to more of that. So thank you again to our guest speakers, and we'll post this the video of this session to the Google Groups list, and I'll create a YouTube playlist for these topics and edit them and get them up hopefully in the next 24 hours or so. Is there anything else anyone would like to add while we're here? I'm just checking the chat again. And I'm not. So hopefully I've gotten everybody's affiliations correct. If not, I posted the link already into the Google group, and we can correct it from there. So thanks again, everybody, for attending, and we'll be back again in another month.
Okay. Thanks, Diane, for organizing this, and see you again soon. Bye-bye.
Thank you, guys.
Thank you, Marcel.
Thank you.
Everyone. Goodbye.
Thank you, everyone.
Have a nice day.